So good morning, good afternoon, everybody. Thank you for joining in. Welcome to this webinar today, which is about the JASCO acoustic monitoring for Slocum gliders. I will just need to inform you that this webinar is being recorded. And a special warm welcome to John Maloney from JASCO. John is the Engineering and Business Development Manager for JASCO Applied Science. John will talk about the collaboration between Teledyne and JASCO today and how they have used the Webb research Slocum glider in their work. John is a passionate advocate for providing marine business with the required information to enable them to conduct their marine industrial activities with minimal environment impact. And John also is on the water outside of business hours in his holiday home. There will be possibilities to ask questions. Please put them in the chat. And for the expert panel, we also have Clara Hubbard from Teledyne Marine. And Clara is a lead on the Slocum gliders in Teledyne Marine. She has 18 years of experience in AUV and buoyancy engine vehicles. So welcome to you, Clara. And I'll hand it over to you, John.
Okay, thanks. Can you hear me?
Yes.
Okay, terrific. Okay, so thanks everybody. Really pleased to be here today. It's very exciting. I guess this is a little bit of a debutante event for OceanObserver and our work that we've been doing with Teledyne Webb research. You know, we're ecstatic about it, and so thank you for Teledyne Marine to be a great partner in promoting not only Slocum but our novel offering for acoustic monitoring. So my presentation today basically will consist of the following. I'm going to talk just briefly for a few seconds about JASCO Applied Sciences. I'll talk about our partnership with Teledyne Webb, and then I'll dive into the technology. And then for an example, I'm going to go back to a deployment in the Gulf of St. Lawrence in 2018 that was a trial and demonstration of this technology. And we've used that data quite a number of times to basically enhance our product and really drive down to the capability and performance of it. And so it's a very useful sort of set of data to talk about. So I'll spend a bit of time on that. And then I'm going to have a session where I answer a bunch of frequently asked questions. I seem to deal with the same questions over and over again from potential partners and clients. And so I'll just do that, and I'll explain how you can help and how you can maybe participate in this interesting technology and an initiative that we have going on. And I'll provide some references and say thanks at the end, of course, and then answer some questions. So I'll talk a little bit about JASCO itself. JASCO Applied Sciences has been in business for over 25 years. And our focus is acoustics, environmental acoustics. And we're in the business of allowing people to do their business in the oceans, but do so in an environmentally friendly way. And so, and we do that for the full life cycle. We help clients and customers get through the permitting phase, you know, the predictive phase where they look at what's the effect of noise going to be on marine environments. We also do acoustic measurements in the ocean. We do monitoring programs, which are really long-term measurements. And probably the most important thing we do is we do a lot of analytics. We collect petabytes of data, and we're able to go through that data both automatically and manually and provide informational products and reports back to clients and customers. And it's that ability to do the analytics piece, I think, which is really is the enabler in this OceanObserver offering. We also produce products and systems, and we have a global presence and capability, and we work all around the planet, mostly in marine construction, oil and gas, renewables, offshore wind, government and academia, and we do some work in defense too. We have a fairly large staff now. We're over 100 employees around the planet, and we have offices in the US, in Canada, in Australia, in Europe, in the UK, and those remote offices help us interact with clients and customers and service those field projects that we do all around the planet. So a bit about this partnership with Teledyne, which is, I'm so excited about. This is truly a win-win relationship. I think Teledyne is equally, excited about it. So for Teledyne, this is all about selling their incredible capabilities, their incredible vehicles and platforms. And so they sell these vehicles, they sell, our product for us, which I'll explain more fully. But they also install and integrate that product in their vehicle and ensure that, there's a high quality of service and product that, that's delivered to the customer and client. There's also all the associated products and services around the glider, piloting, training, people to use this vehicle and the associated passive acoustic monitoring system. So for Teledyne, they end up with a good partner, with a good product, and they're able to sell vehicles, and interact with customers that are interested in the passive acoustic monitoring game. For JASCO, we're really interested in, providing services and product to clients and customers that want to do passive acoustic monitoring. Yes, selling payloads or leasing payloads is something we're interested in, but I think more important for us is, subscriptions or purchases of the associated back office, verification and validation related to the real-time part of this is really important to JASCO. And analyzing the data sort of post-mission, both automatically and manually, is something that we really want to offer to the clients and customers that move forward with OceanObserver. And we're always interested in scientific and industrial collaborations, and not only that, but associated non-recurring engineering for those customers and clients that need particular customizations of the offering. So it really is win for win. We're really excited about it. I think Teledyne's pleased to have an industrial partner that can provide this capability. So I'm going to move on now and talk about the technology. So the first thing I should delineate is between AMAR and OceanObserver, which we all often call Observer, by the way. AMAR is a really interesting product unto its own, but I'm not really going to talk about it too much today. But it is worth noting that AMAR is our long duration autonomous recording platform, and it comes in many sizes and shapes. It's deployed on many platforms. So, for example, it can be put in glass spheres and PVC housings and Delrin housings, and it's deployed autonomously by itself. But you can also take that same recorder, which is a multi-sensor device, can record up to 16 acoustic channels and support a whole bunch of oceanographic instruments. You can take that same device and you can stick it in a Slocum glider. So if you're really interested in a long-term autonomous recording mission, AMAR is worth consideration if you're going to do passive acoustic monitoring. The AMAR can also do some onboard processing, but that's not its focus. Its focus is really being that incredibly long duration device. So think of it as a 16 channel, 10 terabyte acoustic recorder or acoustic and non-acoustic recorder. And that's kind of where AMAR fits in this. Observers really focus on the real-time in situ processing piece. And although it can also record, its strength is its ability to host applications. So, it's easy to put Linux/Java applications on board this device. And so you can get systems to see that can do all the in situ processing piece, detections and measurements. And so that's really its forte. And the two technologies are complementary. And it's not quite black and white. AMAR can do onboard processing, and so can Observer. AMAR can record, and so can Observer. So the solution can vary depending on what you're trying to do. But the rest of this presentation is really going to focus on the real-time piece, which I'm really excited about. So we're going to spend the rest of the presentation talking about the Observer side of this. OceanObserver. So like I said, it's really focused on real-time passive acoustic monitoring. And the solution is more than just the payload itself, more than what the electronics that go and software that goes on the vehicle, and includes both, that plus the telemetry system to get data to ashore, and the back office, the piece that delivers information to clients and customers. And so it's not just about a payload. It's about this infrastructure and getting information of interest and making sure that the information that's delivered is of high quality. And that's the offering. That's really what JASCO and Teledyne are bringing forward here. So the payload itself is interesting. It comes in various sizes and shapes. In the Slocum installation, the electronic stack that you see on the top left corner with the little metal frame around it is how it goes into a Slocum glider. But it's worth, and you can also see sort of what it ends up looking like in the bottom right-hand corner, where you can see the science bay of the Slocum. But it's worth noting that it does come in other sizes and shapes, and it can go in enclosures like titanium housings and PVC or Delrin type enclosures for other platforms. So it also includes PAMLab INT detection and measurement software as an important component of the payload itself. Drilling down into the actual electronics, it's worth spending a couple seconds on that. Observer is based on this Xilinx chip. It's basically a system on a chip infrastructure. So we have one motherboard that supports Observer. Where AMAR G4 is based on the Texas Instrument chip, and it's another motherboard. And then what we have is a suite of daughter cards that we can plug into those two motherboards. It's a common set of hardware. And so we have various digital analog converters, devices that support peripherals, provide power, collect analog information from them, collect digital information from them. There's control lines. There's 3 different types of clocks. There's a wireless controller, and there's a digital analog converter. And you can take these daughter cards and you can plug them into Observer or AMAR, and you can configure them for a particular application. And so it's a very compelling solution. And one of the cool things that I like about this approach, this modular component-based approach, is if you come along with a particular sensor, or you want to, your ADC needs to be slightly different than the next guy's analog to digital converter, we don't have to throw away the entire board stack. We can simply design a piece of electronics for your requirement. So if you want more than 16 channels, for example, it would be possible to spin a one daughter card that could service 8 channels, and you could probably get 32 channels in the Observer board stack quite easily at relatively modest cost. And so it's like I said, it's worth understanding this this infrastructure. It's really quite, I think there's real strength in it for sure. Associated with the board stack is also a daughter card or an offboard card, which we call the memory controller. And there's 2 variants of this. There's a 10 terabyte memory controller and a 6 terabyte memory controller. And in the Slocum installation, we typically put a 6 terabyte memory controller in. Now it's up to you whether you populate every slot with these 512 SD cards. But it's it is quite a bit of onboard memory, and that's without data compression, which is in our future plan, or not using 1 terabyte SD cards. And so in the future, as we test and qualify 1 terabyte SD cards and add lossless data compression, I can see the capacity of these 2 systems increasing dramatically, maybe sixfold, in the next couple of years. I don't know why you would need 60 terabytes or, of memory storage, but I don't know. I work with scientists and they always seem to want more memory storage. So I think we've really sort of nailed it on this one. If you want lots of data stored, we can certainly do so. It's hard to show PAMLab INT. It's an embedded application. But I guess the key thing is PAMLab INT is derived from our PAMLab product, which I'm going to explain a little bit later in the presentation. But the key thing is PAMLab is our detectors and measurement algorithms. And the INT version is headless. It doesn't show you these contour detections that I'm showing here. It actually runs these behind the scenes on board the embedded computer and derives the informational products that that are sent by the payload to shore. So obviously you don't need a graphics interface on board the embedded computer, but the key thing is it's representative of a subset of all the detectors and measurement algorithms that are available on PAMLab. By the way, these are North Atlantic right whale calls, and this is what analysts would see ashore. They don't actually see grams, they actually see images that depict the spectrograms, and this is what they have to do their classification work from. And this concept of sending contour detections, as opposed to some of the other methods, I think is very strong and very compelling. I'll talk a little bit about Slocum integration now. So I've given you sort of a background on the payload at a very high level. We send that payload from JASCO to Teledyne to be integrated into the vehicle. So some of the things that are tackled at Teledyne, or we tackle with Teledyne, are hydrophone mounting. And there's all sorts of methods of doing this. And I guess I'll be a little bit frank here. I think there's room for improvement and room for research related to hydrophone mounting. We've put hydrophones on the wingtips, on the tail, and on top of the vehicle, like you see here. We're doing work on trying to reduce flow noise, but this is something that Teledyne does with the vehicle. Is they also work on hydrophone mounts, and they've done some pretty novel things in this domain for sure. One of the things that both JASCO and Teledyne are working on is on directional processing or directional sensing from Slocums. And there's a number of methods of doing this. You can use vector sensors, you can use compact spatial arrays like this, and there's other methods too. And this is an example of one of the things that Teledyne's offered to one client or customer or a couple. And this is a compact spatial array of 4 hydrophones that can be mounted on the Slocum. And I know there's many other sort of initiatives out there in the world where people are mounting different sensors and putting them on the vehicle. And I guess from JASCO's perspective, because our observer board stack has so many channels and can be configured for different sensors, we're interested in all these types of things, and we believe our system can support them. So if you have a vector sensor that you want to try, or you want to have a towed array off a Slocum, or if you want a compact spatial array like this, we believe our system can support that. And so, I think that's pretty exciting. And like I said, Teledyne would be keen to help you get those sensors and platforms sensors on their platform. We've done a fair bit of work and thinking about how to interact with the mission computer on the glider. And one of the key things that we've learned as we've gone forward is it's really important that the metadata associated with the vehicle be recorded with the acoustic data. And by the way, this list that I'm presenting here isn't complete. There's some proprietary stuff that we're doing that goes beyond this. But the key thing is we send a bunch of metadata associated about the Slocum over to the OceanObserver to be recorded with the acoustic data. And then we send some information from OceanObserver detections, ambient noise measurements, status information back to the Slocum. And the Slocum can use that to make decisions, act autonomously, or send that information on ashore to stakeholders and decision makers ashore. The Slocum controls the OceanObserver. It turns it on, it turns it off, it can shut it down, there's a bunch of commands that the Slocum can send to the OceanObserver, and conversely, the OceanObserver can send requests to the glider. And so this level of integration is really quite, I think, a bit novel, and I think is shows a lot of promise. I think there's a lot of enhancements and improvements we can make in this in the future as we move forward with this offering. So the telemetry of detections and measurements is one of the pieces of integration and a key piece of work that we've done with Teledyne. And so we make use of the Iridium system on board the glider. And so what we have to do is that system is relatively narrow bandwidth. And so we have to reduce the amount of information. And so on board the OceanObserver, we've done a bit of novel work trying to think about how best to send high priority information, the information that decision makers need ashore. How do we get that through that very small bandwidth connection to shore? And so we use this method where we basically group detections. We group them as ensembles, and we have a whole bunch of ensembles built out, and we rank them. We prioritize the ones of most interest. And so what we've done is we've done that so far using species at risk kind of criteria, and we say these are the ones that people want to know about. And normally these days it seems it's all about North Atlantic right whales, or on the West Coast, I guess it's southern resident killer whales. But trying to get those detections to shore is really critical and really important to researchers and decision makers. And so we try to send those ones to shore first, and then try to squeeze the rest of the ensembles to shore. And they're squeezed into very small binary packets, which are transmitted over the Iridium SDB interface, SBD. Talk a little bit now about the back office. Again, a back office is really a bunch of computers, so it's not too exciting from a graphics perspective. But the first component in the back office, I think, is that should be recognized as PAMLab. So PAMLab is this automated and manual analysis tool that we use, and we can run either full PAMLab with its graphics interface, which allows for manual annotations, and also allows us to run a whole bunch of detectors and classifiers and measurement algorithms. And so on board the glider, we can run a subset of those same PAMLab detectors in real time. During post-analysis, we can run this tool, and we can run a much broader set of detectors and classifiers and measurement algorithms in non-real time. So this is the tool that we use when the glider comes back, and you take those SD cards out of the OceanObserver. Now you can use PAMLab to basically do this, do the same types of analysis that was done in real time. You can do it in non-real time in post-analysis. So PAMLab is a key component in the back office, and it allows you to compare what was seen in real time from a subset of the detectors to what you can do with full analysis and that an extra sort of scrutiny of manual analysis. And the other component, both the system on board the glider, the payload, and PAMLab when it's used ashore, at the end of their use, it produces a bunch of detections and measurements. And that's all interesting, but what you really want to be able to do is visualize that. And there's sort of two ways we do it. One way, we email out those detections and classifications. They're converted to graphics, and they're emailed out to analysts for verification and validation. And the second way, we allow stakeholders and analysts to interact with the data is we have a web portal, and we allow them to look at it, visualize it, navigate it, and share it in a visual method. And so, just like you would expect, there's spatial displays, temporal displays, the ability to click on a particular detection, and this is a deployment of a Slocum. The yellow dots represent probable detections. The red dots represent verified detections. And you can click on those dots and you can get the metadata associated with the detection, and you can navigate to those temporal displays and those events themselves. You can actually look at those contour detections. And it's hard, like I said, it's a little hard to show you a website in a static presentation like this. But this is a very important part of the back office, is this ability to navigate and visualize these, the detections that are occurring at sea in real time. This infrastructure, or web portal, which we call Port Listen, is a secure and scalable web portal. You log in, you use credentials, you can only see the data associated with your project. You can navigate it by mission. You can navigate it by your credentials, I guess is the way to say it. And so it is a very compelling compelling way of looking at the data set. And like I said, it's not just about the payload, it's the ability to handle the data ashore. So I'm now going to sort of dive into the Gulf of St. Lawrence trial and demonstration and talk about performance. So the background on this was more or less, a huge event in 2017 where, almost 10% of the population of North Atlantic right whales died in Canadian and US waters. And JASCO really wanted to get involved in this. We really wanted to help. And so we asked how we could help. And I guess the way we were told that we could contribute is really focus on the Orpheline Chaleur Basin, and if we could do real-time monitoring and send a glider into that area, that would be of interest and help to the community, the research community that was looking at this problem. And so we joined with Teledyne Webb, and we had support from Dalhousie, both the Taggart Lab and the Ocean Tracking Network folks, and some funding from the University of Victoria. And we set off to do a glider mission in the Gulf of St. Lawrence, and that mission took place over about a six-week period in the fall of 2018. And like I said, we collected some data. We only actually recorded data for the first week. Unfortunately, we only fitted the observer with 4 SD cards. That was a mistake, but in any case, we were able to record the first week of the trial, which has provided us some incredible data for basically testing and evaluating the performance of an observer. And the way the trial went, we deployed off Chaleur. The glider, flew out to the Orpheline Trough, and so it was a very shallow area. So there's these repeated 50-meter yo-yos as the glider made its transition out to the Orpheline Trough. Then we transited north in the trough, and then transited south in the trough, and we repeated that for the next 6 weeks. And the dives in the trough, were of course deeper, 250 meters, and so you can see basically this is a 1 dive cycle, and you can see that we had a pump CTD running the whole time during the dives, but not during the ascents. And so the quiet periods for us in terms of sampling and looking for detections were during the ascent of the glider, which is not always the case. Sometimes diving is a bit better, but you can imagine over 6 weeks we were able to do a bunch of stuff. And so the information that came to shore from this deployment is really indicated on the bottom, the contoured indications that I show here. The associated spectrograms are at the top just to give you some indication of what the analysts were seeing. So these were coming, the information that you see on the bottom were coming as emails to the analysts, and the analysts were looking at these and making calls, whether it was a valid detection, whether it was a probable detection, or whether it was an invalid detection. And they were basically voting on this using voting buttons in an email application. And their votes were aggregated, and that would decide whether it was a probable or definite detection. And so we were looking for right whales, we were looking for fin whales, We were looking for minkies. We were looking for blues. And sometimes we detected glider noise, so we did get some false detections, and not surprisingly, because the glider does make self noise. And of course, there was other anthropogenic noise in the water, and so we would get some false detections, obviously. The analysts followed this rigorous written down procedure for making that decision, whether it was a possible detection or a valid detection. And there's about 4 pages of these kinds of graphs that sort of document the process that the analysts were following. And I'm no biologist, but I can tell you that it was rigorous. And one of the things that's sort of keynote here is, we really wanted to, when we made a call and forwarded that information to the stakeholders, we wanted it to be correct. It was very important that the information be valid. So when we said there was a definite detection, we wanted it to be a definite detection. We forwarded, and when we made those calls, we would forward it on to this application called Whale Map that Dalhousie University hosts, and most stakeholders here in Atlantic Canada use for looking at these types of surveys. And in this case, you can see our glider is on the left-hand side here, and there's another glider that the Sea Otter folks had deployed following a different track. But we were definitely being pessimistic, I guess, in our calls, whether we had definite detections or probable detections. And this is the actual data from the trial. So let's see here. I don't know if the slide advanced here. I'm gonna have to, excuse me for a second. I don't think the slide advanced. I'm going to have to fix this. Apologies. Okay, so sorry about that. So one of the things that we worked on was getting to high precision. And the reason for that is because the stakeholders in this data set are closing fisheries and rerouting ships, and perhaps, if eventually for other clients and customers, interrupting like wind farm construction. And so precision really counts. And so our detectors and classifiers were biased for high precision. Recall, is really more important when you're studying marine mammals and habitat use. You want to understand, the percentage of detections you've captured, where precision is all about the percentage of detections that are correctly classified, correctly identified. And so, like I said, for this particular trial, we were really focused on high precision and less so, I guess, on recall. And understanding those statistics or the precision and recall that we achieved was an objective for us in this trial. And so we had our analysts here, our biologists, go through the data set, and they manually, went through a full week of data or whatever the recorded period was, and they looked for actual detections in the data set. And you can see that basically, in that data, there was right whales presence, virtually most of the time that the glider was flying in that first week of recording. And same with fin whales. There was less presence of minkies and blues, okay? And we have great confidence in this data because it's now manually annotated, and we can use that as a baseline for comparing the performance of our detectors, as we develop them and improve them. So here's the results that we've been able to achieve from that data set. And you'll see that the precision of 1, which is, either by email, hourly, or by dive or daily, we've been able to achieve that. And so we've got incredibly high precision from the detectors that we're running here. I guess the one that's not quite there by email is minkies, but we really didn't have that many to look at. And on the recall side, our recall is performance is not quite as good, And I think there's some reasons for that. One of the reasons is our focus on precision. And the second thing is we were doing some stuff during the trial that associated with self noise, or there's certainly improvements we could make related to self noise and how to handle that. And so since then we've made some improvements, and I think if we went to sea today and repeated the same trial, and we would get much better results on the recall side. So we're pretty pleased with this, and this is documented in a paper. I'll provide you the reference here in a few seconds. Frequently asked questions, and how can you help? Well, here's I'm just going to rip through this real quick. So if you already own a Slocum glider, yep, we can certainly install an observer in your glider. So just contact Teledyne Webb, and they'll be happy to provide you a quote. That's the way to do that kind of business. Can we do G1, G2, G3 gliders? Yes, we can. G1's a bit trickier. I'm not going to say, it's a slam dunk, but, and it also depends on what other instrumentation you have in your science bay. Science bays tend to get crowded, and we have to squeeze this instrument in with all the other ones. So it depends, what you have in your glider, but generally speaking, we can retrofit a glider with one of these instruments. I think Teledyne would prefer if you bought a new glider, but that's just a suspicion. Can you install OceanObserver yourself? Can you integrate it yourself? Not sure. That's worth a discussion, but I don't recommend it. I'd strongly recommend you get Teledyne to do it for you. That way the glider is going to work, and the OceanObserver is going to work. So my recommendation here is don't do that. By the time you fight with it, you're going to spend more money than it would cost you to get Teledyne to do the install itself. Another question is, can you use JASCO's back office? Absolutely, that's what it's designed for. So you can get a subscription to the back office, or yes, you can purchase the back office you want. We could roll it out to you. We haven't done that before because people prefer the subscription side of this. But if you really insist, if your enterprise is such that you want to be behind firewalls and you don't want your back office exposed to the internet, well then yes, we can install a back office for sure. Can you use your own back office or your own mapping function? Absolutely, for sure. And there's many places in our back office where we can plug into your back office. So yes, that's not a problem and not a showstopper. Can you purchase PAM Lab or PAM Lab INT? Yes, we've sold both in the past, and there's sort of different levels of PAM Lab and PAM Lab INT, and so that's worth a discussion. If you're interested in that, then you should contact JASCO Applied Sciences, and we'd be pleased to talk to you about that. Can you add your own detectors or your own software? Yes, that's certainly possible. There's kind of two ways to do it. One way is we provide APIs that allow you to plug into the data that's coming out of the front end of our OceanObserver. And the second way is, it's not quite there yet, but we're developing a method of allowing customers and clients to play with our detector templates. And in the future, that's going to be probably a supported part of the offering, is you'll be able to add you'll be able to add or create your own detection templates that you can put into OceanObserver. Can you use your own hydrophones or vector sensors? Absolutely, for sure. We've used at least 3 or 4 different types of hydrophones with OceanObserver, and we certainly plugged it into various vector sensors. So yes, that's not a problem. How long a mission is possible? What duration can you get? Well, our math says that a 4-month mission is possible on extended lithium batteries. I think this is an area where we need a bit more feedback from our client community to tell us what they've been able to get out of the system. But there's certainly ways of operating the glider to get longer duration missions, and I'm sure Slocum, I'm sure Teledyne has a few tricks for extending Slocum life on missions. Can OceanObserver send raw acoustic data to shore or to nearby vessels? It can, but obviously that's highly dependent on a telemetry link. So, we're only able to send data over whatever telemetry link is available. If we're cabled to shore or have like Wi-Fi, then obviously sending raw data is possible. But I don't think you really want your Slocum, cabled to shore. So anyway, there are ways of getting raw data off OceanObserver for sure. And can it be installed in other vehicles and platforms? Yes, absolutely. We're doing unmanned surface vehicles, buoys. It's a very versatile tool, and we're using it in all sorts of places. How can you help? Well, I think the main thing is join the club. The more people that are deploying these systems, the more feedback we get on it, the more we collaborate and share the data sets, and the better the product will be, and the more interested that Teledyne and JASCO will be in investing in it. I just had a note today from JJ Park in Korea saying that he's deployed his system. I'm really curious to learn more about his deployment. Here's a Graham from a deployment off the Canary Islands by the University of Las Palmas, Gran Canaria. Yeah, so the more players, the more fun it is, and I think the more the offering can mature into the future. There's also sorts of place for research collaborations here, new and improved detectors, various sensors and sensor mounting, like I mentioned before. Improvements related to self-noise and reducing false detections. I think that's an area of future work and future research. We're doing, like I mentioned, we're doing lots of work on directional sensors and processing, and there's certainly room for more collaborations there. The use of multiple gliders or multi-platforms in localizing marine life, I think, is a really interesting problem, really tough problem, and the more people that work on that, the better off we'll be. And we have several researchers using this technology for basically doing the acoustic localization of the glider. And so work in localizing the glider acoustically, I think, is another area of research or potential research. I've provided two good references here. The first one, is really related to the technology and some of the work that was done in the Gulf of St. Lawrence. And the second one is really more sort of related to the performance of the system. And these two references, I think, are really, really good and useful for coming up to speed on OceanObserver, the technology and its performance. So I'll just put a plug in here. If you haven't been to the JASCO website and looked at our publications page, there's some tremendous publications related to AMAR G4 in both our real-time work using observer in cabled observatories, or other scientific publications. It's really a tremendous resource. So check it out if you have time. There's my contact information, and I just want to thank. I'm just a bit player in this thing. I've been sort of leading the charge and trying to get us to do business with Teledyne, but there's so many gifted colleagues here at JASCO Applied Sciences that have helped develop this capability. We had some help from ACOA initially in the development of the technology. Dalhousie has certainly helped us along here, the Sea Otter folks and the Taggart Lab, the folks at University of Victoria, and I can't say enough about the support and cheering and help and cajoling that we've got from Teledyne Webb Research. I know they're really excited about it. They've sold a whole bunch of systems, gliders, and OceanObservers in the last year, and it's been so exciting to work with them. And we're here at JASCO Applied Sciences. We're looking for a bright future with this endeavor, and we think we're just started on this, and it's just so tremendous. And thank you so very much. And that's the end of my presentation.
Thank you very much, John. That was very interesting. Even though you took time to answer a lot of questions. Down here. Thank you, John. We still have some coming in over the chat, which I will read to you. So the first question that came in is, what is the possible limitation for the long-time monitoring with Observer?
Yeah, I think that goes to the duration question. And so I think like I said, it depends on how the glider is operated. If it's doing a lot of yo-yos, if it's in shallow water, it's going to use a bit more energy. We've postulated and think that missions of up to 4 months in length are possible with extended lithium batteries. you know, that warrants for further testing and maybe a bit more data analysis, but that seems to be what's being indicated by our work to date.
Okay, thank you. Next question. What is the gain and the SNR of the system observer?
Oh, geez,
In brackets.
that's a tough question. And I'm probably not the best guy to answer that, but we typically put hydrophones that have a 165 dB micropascal hydrophones on it. You can certainly put hydrophones that are less sensitive on the OceanObserver. And the noise floor, I'm not going to state that number. It's in the literature in the references that I provided, but I can tell you that maybe if Pete's in the meeting, I'm not sure if he is or not, he can talk about the data quality, but the noise floor is tremendously low. It doesn't vary with sample rate. We arrive at all the sample rates through decimation, and that allows us to keep the same noise floor at all sample rates. And so I just invite you to take a look at the literature as opposed to me trying to do this by memory. I can't remember numbers off the top of my head. I apologize.
I think that's quite okay. The next question is, which is the best way to manage or mitigate the CTD self-noise?
This will sound like a blatant plug for a Canadian company, but our RBR produces a non-pumped CTD, and so I strongly recommend, if you're looking at OceanObserver for a new glider, that you take a look at that particular CTD. That helps, and you can certainly work with Slocum to configure the CTD to only run at certain parts of the die cycle. So I've heard that some researchers run their CTDs only on the first yo-yo and only on the first descent. And then for the rest of that, a single dive, they basically have the CTD turned off. And certainly, so I think it's a combination of technology and how you operate the CTD.
Thank you for that answer. Next question, can we program the observer to record in specific time intervals?
That's a great question. AMAR is designed to do that. It's, duty cycle like that and have very complex duty cycles. Observer less so. And so the way that's accomplished is we get the glider to turn observer on and off. And so it's not as clear cut or as clean as with AMAR, but it certainly is possible. And this is an area where we're actually doing some technical investigation whether we can actually have a daughter card or use some method to actually allow observer to do that itself. But as it currently stands, you do that via the mission computer.
Okay, and this is actually the last question. I have one more question. That would be the last question. I don't see any other over here. Okay, so the last question here is, are there any significant regional considerations for mammal detections, i.e. will a fin whale in North Atlantic waters have the same signature as one in the Southern Hemisphere?
Okay, good question. And it goes to configuring observer. So as I kind of mentioned, we only can put a subset of the PAM lab detectors and classifiers in observer. And so what we do is we down select a set of detectors and classifiers based on, where the glider is going to be used, time of year, species of interest, what are the priorities of the stakeholders in the mission. And so, part of the answer is it tends to be very regional. And so, yes, there are subtle differences between how various species vocalize, and we have to make sure that we have the right detectors and classifiers for a particular mission or a particular employment of the OceanObserver. I'm no biologist, but that's I believe that's the case. And if there's a biologist out there that wants to take a better shot at that question and answer, please go for it.
Okay, so that was the last question. I've just got a request from Pete. Pete First is also with us from Teledyne. If I could open his, let me see if I can. So he would like to have a, yeah, there you go, Pete.
Hi, Helen.
Hi.
Can you hear me?
Sorry, yes, I can.
Hi, everybody. This is Pete Furs. John and I have been working together for 4 years now, since I was the Apex product line manager, and we did an initial R&D project. More recently, we've worked together to integrate Slocum onto a number of gliders for a U.S. Navy customer. Excuse me, and they were collecting ambient noise data. I had a chance to look at that data, and it's incredibly useful. This was the real-time 1/3 octave band, 1 minute integration interval, as opposed to the marine mammal monitoring that John's mentioned already today. But the quality of the data from glider to glider, they virtually overlaid each other. Also, the recordings were great to be able to go back and listen to the full audio data set. And as John said, the glider pumps and pitch battery motor at inflection last about 3 minutes to 4 minutes. Once you're outside of that window, the data quality is fantastic, and you can hear remote. In my case, I was hearing distant Navy ship hull-mounted sonars. Another thing we could hear is the thruster. When the glider thruster is turned on, that impacts the low frequency end of the data set. But the operator knows and learns how to use those things to minimize the impact on the noise data sets. It's a great tool to operate on the Slocum, and we have others who are interested in using it on the Apex profiling floats. So that's all I've got. I wanted to comment in response to John's earlier request, and thanks, John, for a great presentation.
Yep. Thanks, Pete, for your endorsement. That's really fantastic. I really appreciate it.
Okay, so we don't have any more questions. John, if you have anything else to add or comment?
No, I think I just want to thank everyone, especially all the people that were doing the promotion of this this seminar, and obviously, you know, putting together the presentation and helped out with you know, making it happen. I really appreciate the promotion of Observer, JASCO, and Teledyne Webb that's going on here. It's fantastic for both companies. It's truly win-win, and thank you very much for everybody for your contributions.
Okay, so thank you very much, John, for this presentation, and thank you all for listening in. And this has been recorded, as I say, so you can always go in and listen if you want to hear it again. So thank you, everybody. Bye-bye.
Bye.